Hello everyone, we want to look at chapter 2. In chapter 2 we're talking about attenuating networks. So the aim is for you to understand what are attenuators and how we can use them to reduce signal levels in telecommunication equipment. And then for the objectives is for you to be able to identify the various attenuators and their characteristics. So let's start. So attenuation in general refers to the reduction of signal strength. So whenever we have our signal strength decreasing, we call that attenuation. For example, if we start with 10 watts and then end up with 5 watts, there is a loss. So basically attenuation is a loss. So in our case, we do not talk about attenuation in watts, we talk about attenuation in decibels. So attenuation is loss of communication signal strength that is measured in decibels. There are several reasons why a signal can be attenuated. Number one, we can talk about range, the distance in which the signal travels. Over longer distances, both wired and wireless transmission gradually dissipate in strength. And then interference. Some signals might interfere with our signal, causing some interference, hence reduction in signal strength. So radio interference or physical obstruction, such as walls, dampen communication signals on wireless network. Then the wire size. Thinner wires suffer more attenuation than thicker wires on a wired network. This is because of the increase in resistance as with the reduction in size of a wire. Then lastly, we'll talk about attenuators. Actually, attenuators are circuits designed to reduce signal strength. So with this circuit, we actually intentionally introduce it into a circuit so as to reduce our signal strength. So those are some of the reasons why attenuation occurs. So in this chapter, we're mainly going to focus on attenuators, which are circuits designed to reduce signal strength. The attenuating network must consist of purely resistive components to avoid what we call attenuation distortion. Our attenuators, they consist of only resistors, because resistors, the characteristic of our signal when it passes through a resistor, it doesn't change with changes in frequency. So which actually means that all frequencies are treated the same way when they pass through a resistor, unlike capacitors or inductors. In capacitors, if you recall from electricity, your capacitors easily allow high frequencies to pass, whilst for low frequencies, they introduce a very high capacitive reactance, and also vice versa for inductors. Inductors easily allow low frequencies to pass, whereas for high frequencies, they've got a very high inductive reactance, therefore blocking high frequencies and allowing low frequencies to pass. But for resistors, all frequencies, they are treated the same way. They do not, the resistance doesn't change with changes in frequency. So they are designed to have an input and output impedance. So if the input impedance, which is at the input of your attenuator, is equal to the output impedance, which is the output of the attenuator, these impedances are called characteristic impedance. So these are some of the attenuators that you see with the same input impedance and same output impedance. What I'm saying here is that if the input impedance is 600 ohms, the output impedance is also 600 ohms. But there are also others which are called asymmetrical attenuators, whereby the input impedance is different from the output impedance. the input and output impedances are different, and these are called image impedances. For example, let's say if the input impedance is equal to 200, you can have an output impedance of 500 ohms. So, we'll talk about our passive attenuators. Passive attenuators is a purely resistive network that can be used to control the level of our output signal. Remember, our attenuators, the main function of an attenuator is to reduce signal strength. So it consists of resistors. So these are the two things that we've been talking about. It consists of resistors, and it is there to reduce your signal strength. A passive attenuator weakens or attenuates the signal level of transmission whilst improving impedance matching. So the issue of impedance matching is an attenuator should always have a certain input impedance that is known. If the input impedance is 600 ohms, you can easily connect a 600 ohm signal to the input of an attenuator with 600 ohm with correct matching. When we are talking about matching, we are saying that the impedance, let's say the source should have the same impedance as the load, so that when we connect the two, there is no mismatch. So when the two are facing each other, the impedances should be the same as the output. When you connect an output to your attenuator, the input of your load should be equal to the output of that attenuator, so that when you connect the two, they match. Passive attenuators are electrically connected between the source, supply, and the load, with the amount of attenuation induced being of a fixed amount. This part, basically what we're saying is that an attenuator should have a known attenuation level. So if the attenuation is 20 decibels, we should have that attenuator giving us an attenuation of 3 decibels. So there are three most important things that are required by our attenuator. We should know the input impedance. We should know the output impedance. We should also know the attenuation. And it should give us the correct attenuation, correct input impedance, and correct output impedance. That is basically what we are getting from these points. Passive attenuators design can be either fixed, stepped, or variable. So we are going to consider fixed attenuators mainly, but for variable attenuators, basically what we are saying is that you can tune a knob more like your volume, the way you increase or decrease your volume. You can also increase or decrease your attenuation. That's with variable attenuators. So normally attenuators, they range between 1 decibel and 20 decibels. Then, what is attenuation? Remember, attenuation is loss. And in our chapter 1, we covered gain and loss. So, because we already know that we are dealing with loss in this chapter is dealing with loss. We're also going to look at another chapter on amplifiers that will deal with gain. But in this chapter, we're mainly dealing with loss. So attenuation is given by the term D. So because you can see this formula, it's familiar. The only difference is this part. We're saying P in over P out. But in our first chapter, we're saying P out over P in. This is only because we already know we're calculating attenuation, which is loss. We already know that we're getting loss. So, instead of us getting a negative value, we can get a positive value by inverting these two. It is the same formula. The only difference is here we've specified that we are going to calculate loss. So, our values if it is P out over P in, you get negative values. But if it is P in over P out, we get positive values. It doesn't mean that it's a gain. It's only that we have defined that we are calculating loss. Or you can use the voltage ratio, 20 log V in over V out, where P in is the input power, V in input voltage, P out output power, V out output voltage. Note that attenuation is a loss and P in is greater than P out. So we have a factor of attenuation known as N, which is attenuation factor. So in order for us to get that, our attenuation factor should be equal to root P in over P out. And then if you know your logarithm, if you square this part, if you root this part, in order for you to cancel the effect, you can multiply by 2 to get 20 log root P in over P out, where this part is equal to N. So attenuation D is equal to 20 log N. Fortunately for you, you don't have to claim this because we're not going to do calculations for this chapter. Types of attenuators. We mentioned that attenuators can be symmetrical or asymmetrical. Symmetrical is R in is equal to R out. Asymmetrical, R in is not equal to R out. We can also have what we call balanced or unbalanced type. I'll explain this as we look at the circuits. So, common types, we've got the T-type, the pi-type, and the bridged T-type attenuators. Again, you are going to see this as we look at attenuators. So, the first one is the L-paired attenuator. The L is just coming from the fact that we've got one series and one shunt resistance. One series resistor, one shunt resistor. So this is called the L-paired attenuator. We've got R1 and R2. With these types of attenuators, there will be normally they are asymmetrical. The input and output impedances are different. So we've got here what we call an unbalanced, and then we have what we call balanced. With the unbalanced, you can see that we've got this. This is called a series arm. This is also another series arm. This is called a shunt arm. So we've got two series arms. On these two series arms, you can see that one series arm has got a resistor and the other series arm has got no resistance. This is called unbalanced. So if you want to balance, you've got one series arm with a resistor and then the other series arm with another resistor. So these resistors, they are equal. R1 is equal to this R1. And then you've got your shunt resistor. So by converting to this, you would have balance. I normally say half of kusenga kwedonkey. Both series arms should have the same impedance. This is called a U because it's of this shape, as you can see as I'm moving my pointer. So this is an L-paired attenuator. So the L-paired attenuator is the simplest attenuator design, consisting of only two resistive elements and is more commonly known as the voltage divide. If you can go back a little bit, voltage divider. This is a simple voltage divider circuit with two resistors, R1 and R2, whereby these two can share the voltage. Whatever you have here is distributed between R1 and R2 depending on the ratio of those resistors. The L-paired attenuator is an unbalanced asymmetrical attenuator circuit that can only impedance match in one direction. So what it simply means is that you can only you can match your input of the attenuator to whatever source is connected to that input. That's one direction matching. And you can only match your output with the resistance of that output. So the balanced equivalent output is called the U-pad attenuator. Then we've got the pi type attenuator. The mathematical pi is taken because of the shape of these three resistors. So in this we've got the unbalanced again. As you can see, the series arm, only one arm has got a resistance, whereas the other arm doesn't have that resistance. That's why it's called unbalanced. And then in order for you to balance it, you have to share this resistance amongst these two arms, making it more like an OR-pad, an OR configuration. So again, the series arm should also have the same impedance with this series arm. Normally, when you say this, it means that they are symmetrical. The impedance of this part is equal to the impedance of that part. The input impedance here is equal to the output impedance here. So a pi-type attenuator is called because of that. The resistors, they form a pi configuration. The pi-pad attenuator is most commonly symmetrical, like I mentioned. Passive attenuator that can be used between equal impedances or impedance matching between equal impedances. So we're simply saying that normally it is found in between two devices. The attenuator is found between two devices of the same impedance. A single pi-pad attenuator can achieve much higher levels of attenuation compared to the equivalent T. Alright. The balanced is called the OR-pad, like we mentioned. So let's look at the T-pad attenuator. The T comes from the configuration. These resistors, they form a T. So this is unbalanced again because this arm have got resistors R1 and R1, whereas this arm doesn't have any resistance. And the T comes from the shape, which is the T configuration. Again, this is a symmetrical attenuator, whereby the input impedance is the same as the output impedance here. And you can match between the two devices. So, in order for you to balance, you have to share the resistance R1 on both arms. So you have got R1 over 2, R1 over 2, R1 over 2, R1 over 2. Whereby this arm will have the same resistance as the arm. So it forms a letter T, and it is symmetrical, which means it can be used between equal impedances for impedance matching. Again, in order for you to balance it, it forms an H configuration. So we also have what we call a bridged T-type attenuator. A bridged, this is the T with the bridge resistor R3. This is a bridged, unbalanced bridged T-type. If you want to balance again, whatever you have here, you divide it by 2 and connect it to the other series arm. Again, they are symmetrical. This impedance is equal to that impedance. These two impedances are the same. So A bridged T-type attenuator is a variation of the standard T-pad design, which has an additional resistive element forming a bridged network across the two. As you can see from this R3 is variable. Take note, R2 is also variable. Okay. So a bridged T attenuator is a variation on the standard T-pad design, which has an additional resistive element forming a bridged network across the two series resistors, and gain its name from the fact that the input source signal appears bridge itself across the T-pad network. So the function basically of the two variable resistors is for you to be able to vary your attenuation. So the bridged T-type attenuator is symmetrical, purely resistive attenuator, and can conveniently be used as a variable attenuator or switchable attenuator. So here basically we're just saying what is a variable attenuator. A variable attenuator are so designed to have a constant input and output impedance but variable attenuation. Basically a bridged T-type attenuator is a variable attenuator whereby whenever you vary your attenuation, you only vary your attenuation but you do not change your input and output impedances. Okay, so we can go through that. So for summary, attenuators are network designed to lessen our signal voltage or current at certain stages. They are purely resistive, and in order for attenuation to occur, we should have the correct input impedance, correct output impedance, and also it should give the specified attenuation, and then D is equals to 20 log N. So this is the end of our chapter. Thank you.